There's something else that you may have recognized about the enthalpy changes associated with chemical reaction that follows from the fact that phase changes have an enthalpy change associated with them. Going from solid to liquid water costs you energy. And the fact that the conditions of the system dictate how much enthalpy is released in a chemical reaction. And that is, if you run reactions at different temperatures or if you run reactions at different pressures, the enthalpy change that you observe might be different because the phases of the chemicals that are participating in the chemical reaction might be different at different pressures and temperatures. And so as a result, when we are making predictions about chemical reaction, the enthalpy changes for all chemical reactions have to be compared using the same set of reaction conditions for the enthalpies, for us to understand how the actual magnitude of the heat exchanged by a chemical reaction compares between different chemical reactions. So recognize that because enthalpy is a state function, and because the conditions of the system include what phases the reactants and the products are in, phases matter when you're talking about the enthalpy change that you'll see for a reaction, which is another way of saying that the pressure and temperature at which you're running the reaction matter, and they influence how much heat the reaction absorbs or releases. One way to look at this is to consider a combustion reaction where we burn propane, common natural gas fuel source, in oxygen. And the balanced chemical reaction is 1 mole of propane, which has chemical formula C3H8, reacts with 5 moles of O2 to give 3 moles of CO2 and 4 moles of H2O. How much heat does burning propane release on a per mole basis? Well, we can find a thermochemical equation for propane, but immediately we notice something if we go to look up those values. The phases of the reactants and the products influence how much heat is actually going to be released by the system. Now, at most any pressure and temperature that you would burn propane at, propane is going to be in the gas phase, oxygen is going to be in the gas phase, and CO2 is going to be in the gas phase. But depending on the pressure and temperature at which you run the reaction, the other product, water, of the combustion reaction might be in the gas phase or it might be in the liquid phase. If your water is in the gas phase, the enthalpy of reaction is exothermic and it's negative 2044 kilojoules per mole of propane burned. If your water is in the liquid phase, however, although the reaction is still exothermic, it's more exothermic. 1 mole of propane reacts with 5 moles of O2 to give you 3 moles of CO2 and 4 moles of liquid water, is more exothermic, and the enthalpy change for this reaction is negative 2,220 kilojoules per mole of propane burned. Why are they different? Well, one way to look at it is, in this reaction at the top, we've actually put energy into vaporizing the liquid water, which is an endothermic process. The enthalpy of vaporization for water is endothermic. And vaporizing that 4 moles of water from the liquid phase to the gas phase cost us some energy that is now not going to be released to the surroundings because it was absorbed by the liquid water, changing it into the gas phase water. All this is a fancy way of saying that when you're looking at thermochemical equations, you can't just focus on the mole ratios of the reactants and products. You have to carefully also watch the phases, because the phases of the reactants and the products influence how much energy is going to be absorbed or released by the system. So for instance, if you use a table like Appendix G or the other tables in your book to look up enthalpies for a chemical reaction, then you need to make sure that the chemical reaction you're looking up not only has the right reactants and products, but they're all in the phases that you're interested in, because the phases matter when you're talking about how much enthalpy is released. And as a result, when chemists talk about enthalpy changes, we introduce a concept called standard state conditions. The thermodynamic standard state is shorthand. Sometimes we just say standard state. This is shorthand for a specific set of conditions to run a calorimetry or a thermochemical experiment. And the thermodynamic standard state is defined as all the chemicals participating in the reaction are in their most stable phases at 1 atmosphere of pressure and 25 degrees Celsius. If you have any ions or molecular compounds that are dissolved in water, they are in a 1 molar concentration. If you are not running your reaction under these exact conditions, 1 atmosphere of pressure, 25 degrees Celsius, and a 1 molar aqueous concentration for any dissolved chemicals, then your enthalpy is not being measured at the thermodynamic standard state. And the reason chemists define a thermodynamic standard state is that so people have a common set of conditions to which they compare enthalpies that they measure for different reactions. It sets up a framework that we can use as a point of comparison for different measurements. If you're looking at measurements made under standard conditions, your enthalpy, delta H, will have a degree sign next to it, and you read it as delta H naught. We call that the standard enthalpy of reaction. So for instance, if you see a thermochemical equation that says 1 mole of propane in the gas phase is burned in the presence of 5 moles of O2 in the gas phase to give 3 moles of CO2 in the gas phase and 4 moles of H2O in the gas phase, delta H naught for this reaction is equal to negative 2044 kilojoules. And what that's saying is that this enthalpy measurement was obtained at 1 atmosphere of pressure and a surrounding temperature of 25 degrees Celsius. Since this is a combustion reaction, the temperature in the flame will obviously not be 25 degrees Celsius, but the temperature, the ambient temperature at which the reaction is being run, will be 25 degrees Celsius. And so if you see an enthalpy value that says delta H naught, you know that the enthalpy value was collected at thermodynamic standard state conditions. If you see an enthalpy change that doesn't have the degree sign, doesn't have a naught next to it, the thermochemical data was likely collected under different conditions, and so you can't necessarily use it as a point of comparison against a reaction that was run under standard conditions without getting some more information. So be aware of the thermodynamic standard state. Most of the enthalpies that we'll deal with from now on in this chapter, whether they're reaction enthalpies or formation enthalpies, which you haven't been introduced to yet, are going to be collected under standard state conditions. But watch for that naught sign so that you know the enthalpy value was collected under standard state conditions.